Hello everyone. So this video is going to go over an econ example that shows the Lagrange multiplier method in practice. So we have a monopolistic producer producing two goods, 1 and 2, and the quantities that are being produced are Q1 and Q2 respectively, and the prices of these two goods are given by P1 and P2 respectively. Now, the producer has this joint total cost function, which is the total cost of producing both the goods, and that is given by this particular total cost function. And we're given the demand functions for both the goods in terms of P as a function of quantity. So you have P1 and P2. So remember I told you that a monopoly, in a monopoly, the producer is going to have a downward sloping demand curve. So you have P as a function of Q. And just as an interesting tidbit, notice how the demand is not just a, P is going to be a function of Q1 as well as Q2. And similarly, you see P2 being a function of Q1 as well as Q2. So just, that's just an interesting thought to see how demand for a commodity is related to the production of another good as well. Think of substitutes and complements, and this is a great way to even think about cross-price elasticity. Anyway, so far so good. So we have two demand functions. Now we're asked to find the maximum profit if the firm is contracted to produce a total of 15 goods of either type. So we want to maximize profit, but then there seems to be some sort of a condition that follows the find maximum profit part of the question. And so the firm is contracted to produce a total of 15 goods of either type. So one way of reading that is saying maybe the firm in total, the amount of 1 and 2, the good 1 and 2 that it produces, looks like that is capped at 15. So that seems to look like a constraint. So maybe we want to maximize this profit subject to a particular constraint here. So this is a constraint optimization problem. And then the second part of the question asks us to estimate new optimal profit if the production quota rises by 1 unit. Okay, so when they say production quota, we know for certain that this is there is a constraint in terms of the production quota. And if the constraint changes by 1 unit, we want to see what happens to total profits. All right, so let's, so this is a constraint optimization problem. So let's evaluate it using the Lagrange approach. So we want to get the objective function first, which is pi, and that is just total revenue minus total cost. And now this is, there are steps involved in this process. So let's compute the total revenue first. Now total revenue is going to be the sum of the revenue for each of the two groups. So let's compute what TR1 is going to be. So TR1 is going to be price 1 times quantity 1. And we know that P1 is given by 50 minus Q1 plus Q2. And that when you multiply that by Q1, that is going to give you your total revenue. And that is going to be 50 Q1 minus Q1 square plus Q1 Q2. Okay, so that was the revenue for the first one. Let's get P2 Q2, which is total revenue for the second good. This is going to be 30 plus 2Q1 minus Q2, 30 plus 2Q1 minus Q2 into Q2. So we have 30 Q2 plus 2Q1 Q2 minus Q2 square. And when you add these two up, you're going to get the total revenue function. And that is just going to be 50 Q1 minus Q1 square plus Q1 Q2 plus 30 Q2 minus plus 2 Q1 Q2 minus Q2 square. So let me just collect the terms and put this in a slightly neater way. So we have 50 Q1 plus 30 Q2 plus 3 Q1 Q2 minus Q1 square minus Q2 square. So that is going to be my total revenue function. Now we have the total cost function already given to us. So let's go ahead and compute the total profit function. So this looks like it is going to be 40 Q1 plus 2 Q1 Q2 plus 20 Q2 minus Q1 square minus Q2 square. Does that look right? Yes, so 40 Q1 plus 2 Q1 Q2 plus 20 Q2 minus Q1 square minus Q2 square. So that is our profit function, which is a function of Q1 and Q2. This is our objective function. Now the constraint is given that the firm produces 15 goods in total. So overall, the amount of good 1 and good 2 that it produces can be given by Q1 plus Q2. Now the constraint tells us that this is capped at 15. So that will be our constraint. So the problem now is to maximize profits of 40 Q1 plus 2 Q1 Q2 plus 20 Q2, minus Q1 square minus Q2 square, subject to the constraint Q1 plus Q2 is equal to 15. So this is what our problem boils down to. Let's write down the Lagrangian function. The Lagrangian function is just going to be our objective function plus a lambda into m minus g of Q1 Q2. Here m is your 15. Let me put a different color. M is 15. And g of Q1 Q2 is just Q1 plus Q2. So your Lagrangian function is actually just going to be 40 Q1 plus 2 Q1 Q2 plus 20 Q2 minus Q1 square minus Q2 square plus lambda into 15 minus Q1 plus Q2. Or I'm just going to write this as minus Q1 minus Q2. So that is what our Lagrangian function looks like. So we have the Lagrangian function written that way. Now all that is left for us to do is to just take the partial derivative of the Lagrangian with respect to each of its inputs, which is Q1, Q2, and lambda, set that all equal to 0, and then solve simultaneously, and then we're done. So, okay, so what is dou L by dou Q1 going to be? So we have 40 and plus 2Q2 minus 2Q1 minus lambda equals 0. So this essentially translates to 2Q2 minus 2Q1 minus lambda equals minus 40. Let's keep it that way. Let's do dou L by dou Q2. So this is going to be 2Q1 plus 20 minus 2Q2 minus lambda is 0. So this can be written as 2Q1 minus 2Q2. So actually, let me rewrite the first one in a slightly different way. So I'll just put the Q1 term first and then the Q2 term. So minus 2Q1 plus 2Q2 minus lambda is minus 40. That's the first one. Second, you have 2Q1 minus 2Q2 minus lambda is minus 20. We'll keep it that way. The final one, dou L by dou lambda, as I told you in the previous example, that is actually just going to give you your constraint. So you'll actually have 15 minus Q1 minus Q2 is 0. Therefore, 15 is equal to Q1 plus Q2. So we have 3 variables that are unknown, and we have 3 equations. So it is now going to be possible for us to solve and find a solution. So let me just call this equation 1, this can be 2, and this can be 3. Now, if I just add up 1 and 2, I can actually find out what lambda is, because Q1 and Q2 will just get cancelled out. So 1 plus 2, you are going to get minus 2Q1 plus 2Q2 minus lambda is minus 40. Then you have 2Q1 minus 2Q2 minus lambda is minus 20. And when you add up these two, the first term vanishes, the second term gets cancelled, so we end up getting minus 2 lambda is minus 60. Therefore, lambda is just going to be 30. Right. So once you have lambda, what you can do is you plug it into any of the first or the second expression and get one equation in just Q1 and Q2 terms, and then you already have another one, and we can go ahead and solve it. So let's plug lambda is equal to 30 into the second equation. So we get 2Q1 minus 2Q2 minus lambda is equal to minus 20. So 2Q1 minus 2Q2 is equal to minus 20 plus lambda, which is just going to be 30. So you get 2Q1 minus 2Q2 is equal to 10, and we can probably write that as Q1 minus Q2 is equal to 5, dividing by 2 throughout. And then you can just do Q1 plus Q2 is equal to 15, which comes from the third constraint. And then when you solve this, you get 2Q1 is equal to 20. Therefore Q1 is equal to 10, and Q2 is just going to be 5. Because Q1 plus Q2 will be 15, right? So you're going to end up having the following as your solution. So lambda is 30, Q1 is 10, and Q2 is just 5. So these are the optimal solutions. And if you want to find the maximum profit, all that you have to do is just plug in these values and compute the solution. Plus 20 into 5 minus 5 square. So you have 400. So this is 400 minus 100 plus this is what? Another 100. So and then you have another 100 minus 25. So you have 500 minus 25. So the answer is 475. That's the maximum profit value. Now, the second part of the question asks us to find what the optimal profit would be when the production quota increases by 1 unit. That is to say, the constraint now is Q1 plus Q2. It was originally 15, but they're saying that that is now increasing by 1 unit. So this is now 16. So how do we go ahead and solve this? One way to do this is to repeat the entire process by now setting M as 16 and repeating the Lagrangian approach. But that may be a bit cumbersome because all that we want to do is we only want to find the change or the new profit when the constraint changes. So is there a way where we can have a convenient shortcut and where we don't have to end up finding all of these input values once again? Actually, there is. And that shortcut is actually based on the lambda, which is the Lagrange multiplier. And remember I told you in the previous video that when you write a Lagrangian function, if you consider m, if you treat m as another variable in that function and write down the Lagrangian as a function of 4 variables instead of 3 variables, then that is going to allow you to take partial derivative of the Lagrangian function with respect to m as well. And when you do that, you actually just get lambda. So, and lambda here in this case is 30. So what dou L by dou M is actually doing is if your constraint increases by 1 unit, then by how much does your objective or the optimal function, whichever one you're evaluating, how much does that change? So, and remember that when you are solving for all of this, one of the partial derivative equations that you simultaneously solve for, you will be setting dou L by dou lambda to 0. And remember that dou L by dou lambda just actually gives you your constraint. Right? So when m is equal to g of q1 plus q2, this entire term in the brackets will become 0 in the objective function when you are optimizing. Because one of the constraints that you're actually solving for will ensure that your budget constraint is totally met. So this entire second term will vanish. So your Lagrangian function essentially just becomes your profit function. So when I say dou L by dou M is lambda, if M increases by 1 unit, when I say my objective function increases by lambda, it is not just the Lagrangian function which increases, but it is also your profit function which will increase by lambda. And how does Lagrangian become just the profit function? Because one of the optimality conditions is that dou L by dou lambda is 0, which actually ensures that your budget constraint is fully met. So this entire term is now 0. So your Lagrangian just becomes the objective, your Lagrangian function just becomes the profit function. So dou L by dou M is equal to just lambda. And that tells you that when lambda gives you the change in value of the objective function, when the value of the constraint is increased by 1 unit. So this is exactly what is happening here, right? From 15, the constraint is now going up to 16 by exactly 1 unit. So the profit is also going to now increase by 30 units. Therefore, the new optimal profit, sorry about that. Yeah, so the new optimal profit is going to be 475 plus 30, therefore 5. So the lambda or the Lagrange multiplier actually has a very nice property that it tells you when your constraint is being tweaked, how does your objective function change? And this has a big role to play, especially when you're talking about utility maximizing problems with the consumer and you're tweaking the income of the consumer and trying to understand how utility is changing. So all that you have to do is just do dou L by dou M. And there you go. It shows you by how much your utility will change when your income is changing. So that's about the Lagrange multiplier. So I'm going to stop my video here. And for more worked out examples, I'm going to refer you to the textbook. And so good luck learning and enjoy Lagrangian functions.